everyone, good morning. Today I want to continue the webinar series of all the aspects of debugging with the Universal Debug Engine from PLS. And today the topic is Multicore and multi-controller debugging for AURIX. Last week I introduced the tool a little bit, and this webinar will focus more on the technical part and give you some demos. So let's get started. Today multicore and multi-controller debugging, that is the topic, especially for the AURIX microcontroller, which is a multicore system, which is a very popular multicore system running on different automotive and as well as industrial applications. Okay, what is the agenda for this webinar today? At first, I'd like to introduce a little bit how to set up a debug session with UDE. There are some easy steps to do, and then you can start with your multicore debug activities. I'd like to show you how to use some of the typical debug functions for multicore systems, and after that, in the second part of this webinar, I would like to show you how to do multi-controller debugging, and finally, I do a short summary. Okay, let's get started with set up a debug session with UDE. So what you cannot see in this webinar is my hardware setup that is on my desktop here. From the webinar last week, you should know that we have a number of so-called universal access devices that can be used to connect to your target system. In this webinar, in the first part of this webinar, I use a tri-board with an AURIX TC39 and the DAP connector or the DAP debug interface to connect to the debugger running on my PC. You can see it on this picture here. The DAB connector is connected to this little piece of hardware, which is our Infineon JTAG and DAP target adapter, which is a combined adapter using for both debug interfaces that we can use with these kinds of boards here. And this adapter is then connected to the UAD2 Pro, which is our smallest debug box, and this box is connected to my PC using USB. The only target specific part here is that adapter. Our access devices are flexible enough to connect or can be used with all the supported microcontrollers that we support with the UDE debugger. Okay, what is a debug session? The debug session contains all the settings or the views in the debugger or the to be loaded target applications together and saved. And can be saved as a workspace file. So with the UDE, you create a UDE workspace which contains all this information. You can use this file and transfer it to another PC. For example, if you have a lab where you want to test something on ECU, for example, or if you want to transfer it to your home office, for example, to work there, or you transfer the workspace to another user, for example, which is responsible for end-of-line testing or something like that. So the workspace contains several parts. yeah, you can continue the work as you left off. So the workspace is persistent and can be used another day as the same way you used it this day, for example. Okay, the workspace contains a number of things. The first, you have to specify which controller type or which board you want to connect to your debugger. You specify which debug interface you want to use. You have seen it on my example here. I use the DAP from Infineon. I can say, okay, I'd like to see in my debug session all the cores that comes with, for example, this AURIX 39, which are 6 cores, and I can also issue some init commands, which can be used, for example, to set a specific configurations to the target in order to make it debuggable. For example, to disable a watchdog, which would reset the target if the debugger gets connected and holds the application, for example, and something like that. With the target configuration, always we select also the used access device, which is connected to the PC to be used to communicate with the target system itself. And of course, we need some other things to set up here through the user interface guided process of setting up these things. We select predefined target configuration, or we select also the cores that should be enabled. Okay, I said it before, but we have also the application that should be loaded, perhaps as an ELF file or a combination of hex and ELF files. The ELF file contains always the debug information that the debugger is using to present you variables, functions, the source code itself, and everything needed for the debug, for debugging purposes. And also it contains the binary, which is loaded by the debugger to the target, into the flash or into the RAM, depending on the linker settings of the debugger. And finally, the workspace contains also all the windows that you want to see to present you the status of your application, like variables, the source code windows, registers, etc., etc. Okay, then let's get started with the creating of the workspace. This is the UDE, the latest version, just opened and blank, and we start to create the workspace from scratch. We have to do, or we have to create the workspace. We want to use a new workspace or create a new workspace. We click on that menu item, look for a location on your hard disk, or a specific folder where you want to save the workspace file and give it a name, for example, TC39 demo. That is the file or the file name for the workspace, and with this file name you can, or with this file you can move the workspace to another PC or provide it to another user. Then we will ask to for a target configuration. The debugger needs to know which target should be connected. We use a default target configuration, press default, and we get a list of all the supported microcontroller architectures. And we choose a tri-core AURIX 2G, which is the TC3X series from Infineon. And we have a list of all the supported devices. We select the 39X B step. It's a tri-board, a starter kit, and we connect using DAP. And this is a predefined configuration for a multi-core setup using the DAP interface from Infineon. Okay, press ready, and then browse for a folder where we want to save the target configuration file. I use it the same as it used for the Workspace file. Save it, and then we get this here in this list, and I can select that. From here, I can also change some settings here for the target configuration file. For example, if I want to use another access device, I can choose this access device here. For example, I can select out of a list of connected access devices, set a remote access device using or by providing an IP address for remote debugging. For example, if you are in a home office, then you can select a access device attached to an Ethernet port, enter the IP address here, and you can connect to that target. But I don't need any changes here, and select this pre-configured access device or pre-configured target configuration. Then then UDE asks for which course I want to have in the debug session. I can check or uncheck here the course. I leave it untouched in this case. I want to see all the six cores of this tri-core or this AURIX 2G device, but the GTM, which is the seventh core, if you like, a generic timer module by Bosch, that is also it can also be part of the debug session, but I have no sample for that at the moment, and it is also too complex to show debugging of the GTM during a half-an-hour webinar. Okay, then press OK, and UDE is now connecting to the target. We wait for some seconds, and then we get 6 cores successfully connected to the target. Okay, then we need to load the application that should be loaded to the target system. It is located for Flash, and then I get this window here, which tells me, okay, this is the ELF file that should be loaded. The ELF file contains also the binary. It is not separated between a binary and debug information. It's a combined ELF file, so I can use it as it is. For AURIX and for several other architectures or controllers, it is necessary to know which core of this multi-core device is responsible for flash programming or for programming the application to the target. For the AURIX, it's always the core 0. So I have to check the binary loading mechanism for core 0. This is the blue box here. And in this ELF file, for all the 6 cores, debug information exists. So I check the green boxes here for all the 6 cores, because the green check boxes means, okay, load or provide debug information to the debugger for this core or for that core. You can also use this loading mechanism also for several ELF files to be loaded on one target. For example, if you have a multi-core application where for each core a separate ELF file exists, then for AURIX you would check always for these ELF files the controller core 0 for flash programming, and for each separate ELF file, the checkbox for the binary symbols for the assigned core. If you want to load another ELF file, you press that button here and select the other ELF file. Okay, but for this example, it is everything fine. Press OK. Then the application is loaded. Sometimes you get this window to browse in some ELF file, some source files. In the ELF file, there are typically fixed source file paths are provided, and if you move, or if you have another PC or move your application to another location, then these paths are invalid. So you have to browse in the specific files, for example, the startup code here. But if you there's a in the config debug server configuration setting, you can always say, okay, replace some paths here to the present location of your source code files. So then we want to see our some source code here in the UDE. At first, I use the target manager and put it to the leftmost docking container here of the user environment. And the target manager presents you or shows you all the connected cores and the status of the core. So core 0 is in halted state, and the other cores are inactive at the moment. So for AURIX, it's always the case that you have to load your application into core 0, and then the application is responsible for waking up all the other cores. So the application is not running at the moment, so core 0 is halted and core 1 to 5 are inactive. You can see it also here in the top of the toolbar where all the cores are presented using also core colors here. And these boxes are showing you the current state of the cores. I can, for example, start the application and you see all cores are running now. And you see it also here indicated by the green indicators that everything is running. So for the moment, I look for some of the source files for the core 0, and then for the core 1 as well. Dock it on some position here, and okay, also for the core 2 as well. And then I'd like to show you some variables. To open a watch window where you can put some variables, I have to click, or I have to activate the core for which I want to see the variables by clicking in, for example, the source code here, or by activate the core by clicking on the cores here in the toolbar, and I can see here on the bottom in the status line which core is active at the moment. So I activate core 0, open the watch window for core 0, put it here. Then I can change the behavior of the docking and browse for a variable. Enable a periodic refresh, so I can see, okay, the core is running. The same I do for the core 1. put it also here and enable the periodic refresh. And finally, also for this core here, so that we can see that we are running now some and counting something here. Okay, so we set up this and then we can save it. Close Workspace, save, okay. And then we can reopen it. And then we can do just some multi-core debugging. Reload this saved workspace and everything looks like the same. Now the workspace provides us the ELF file, which is part of the workspace. We can press OK. And then we can start the application. If we set a breakpoint, for example, in this second core 1, for example, in the function port update signal, for example, we can press here on this window to, oh, I missed something. I forgot. This is not the right ELF file. That's located for one. Okay. Just wondering, I'd like to have it flashed. Okay. Now the flash tool gets opened to program the application. Okay. So now we set the breakpoint in this update signal. So at the moment we hit the breakpoint. I need to open the breakpoint window, disable it and run it again. And then if we enable it, you see all the cores are running. And we enable the breakpoint, then we hit the breakpoint in this update signal function here in core 1, and all other cores gets halted as well. So that is the standard or the default configuration of UDE for multi-core debugging. So that all cores are synchronized for debugging. Synchronizing means breaking, for example, single stepping, and so on, and restarting. Okay, we don't need this source code here. But if you want to if you want to do an independently debugging, then you can decouple this synchronization by using the run control management, which contains groups of cores that should be part of one run control group and it should be synchronized for debugging. For example, here in this case, we have all the cores grouped together and all 6 cores are synchronized. We can remove, for example, core 1 and core 2 from this group and then disable the breakpoint. I put the breakpoint window here. Disable the breakpoint, and then I can start the core 1. And now you see core 1 is running, but all the other cores are stopped because core 1 is not part of the run control group anymore. If we select one core of the run control group and press start, then core 0 and core 3 and 4 are running as well. Core 2 are also not part of the run control group. I have to start it manually. And now all cores are running. And if I now enable the breakpoint for the core 1, then you see we stop in core 1, but all the other cores remains running. That is the basic functionality of the run control management. If I want to re-enable or reassign all the cores back to the run control group, then I have to stop the complete system, in this case manually, because only on a completely stopped system I can change the run control groups. This is a hardware limitation in this case. So core 0 is running, so core 2 is running, so I stop it, and then I can open the run control management and then add all the cores. Make go, enable the breakpoint, and you see all the cores are now ordered again. Sometimes it is, we have functions in the application which are shared between the cores. So every core is sometimes executing these exit shared function. We start the application, okay. But if I set a breakpoint here in the core 1 and make go and go and go again, then we always see that only core 1 is halted at this function here. So a breakpoint is always only active on a specific core. That is because breakpoints are handled by the debug logic on chip on the specific core. If we want to stop these function here also for core 0, for example, then perhaps you can look for this function here and set a breakpoint as well. And then, okay, sometimes we stop in core 1 and sometimes we stop in core 2, in core 0. But this would be very annoying if you have a 6-core system and you want to stop always in this shared function independently which core is actually executing this function. This is not that what we want. So UDE provides you for this case a so-called multi-core breakpoint. If you enable that, you can do this in the breakpoint window, for example. Then for all the cores of the active run control group, the breakpoints are distributed over all the cores. So now I have the breakpoint here in the exit shared function for all the 6 cores, and if I start the program, then you see, okay, now we stop in core 2, we stop now in core 1, and now in core 0. Of course, you can also add these multi-core breakpoints here using the context menu of the program window. Okay, that is these are the basic things in UDE that helps you to debug a multi-core application. And now I'd like to sum up these things. You have seen that it is very easy to set up a debug session for a multi-core system based on the predefined target configurations. I've shown you how to set up some views, dock windows, open windows, set, for example, periodic refresh for watch window and to refresh or to provide real-time watches. I have shown you how to load an application. In this case, we had a monolithic application with only one ELF file, but it's also possible to load several independent applications to the debug session and to the target. I have shown you some things on the user interface. You have seen that we have all things together in one user interface. There's no need to open debuggers for each core. We have a more system-centric view than a core-centric view with UDE. We have seen that all the windows belonging to one core are colored the same color, which gives you a good overview of the application and the status of your target under test, for example. And I've shown you the synchronized debugging features of UDE, how to break step and single step synchronized using the multicore run control, and how to use multicore breakpoints. Okay, in the second part of this webinar, I'd like to show you how to debug multi-controller systems. Okay, a multi-core controller system typically use not one MCU, it uses typically 2 MCUs. In that case, or in this demo here, I use a board with 2 AURIX TC39 controllers, which are communicating using an HSSL link between the controllers. And for both controllers, there is a separate debug interface available. So why we do, or why we have these type of applications? There are applications in the field of automotive or industrial where we have the demand of high safety that we should meet, for example, AC level D or SIL level 4 applications. These safety is achieved by redundancy by a second controller. Or, for example, fail operational systems like we have here on this picture. This is a electrical power steering demonstrator by Infineon and Hitex, which uses 2 AURIX controllers for this safety critical automotive application. The other use case that we have very often is that we can extend the resources by a second MCU. For example, to add additional computing power to the system by the second MCU, or to extend the number of the available interfaces to the system. For example, in that case, here in this automotive Ethernet gateway board, we have 2 AURIX TC39, which provides interfaces for legacy in-car communication and combines them to automotive gigabit Ethernet interfaces. So both AURIXs provide several peripherals and interfaces, and with these 2 MCUs, we have a lot more available in the application. For these applications, we need some kind of synchronized debugging. And the target or the aim is that we want to debug 2 controllers in one debugger instance in one UDE session. And it should be, the look and feel that we want to have is like a multi-core system. We want to see we want not to separate between these 2 controllers. We want to have it in one debug session and as a kind of multi-core debugging. So we need some kind of synchronization, and for that we provide a piece of hardware, which is the multi-core or multi-AURIX debug adapter, which is responsible for synchronizing the debug functions like breaking, single stepping, or restarting of both of the AURIXs. The hardware setup looks like that. We have our UAD3+, which can connect up to 8 targets using a cascaded design. So we use these boxes, which we call debug pod. Each debug pod has 2 connectors here, and we can connect up to 4 pods with 2 connectors each. That results in 8 targets that can be connected. In that specific case, we connect only 1 pod with 2 connectors. Each connector is connected to one of the DAP interfaces of this dual AURIX board here on the right side. And in between, there is the multi-AURIX debug adapter connected to standard debug adapters from us for the DAP. And what we also need is some kind of synchronizing mechanism using a separated trigger line, which sends break signals or receives status signals from each of the AURIX controllers here. This is the hardware setup that I will use for the demo that is following. This is a gateway board from Infineon. You see here the 2 AURIXs and the connection to the DAP interface. This is the multi-AURIX debug adapter, the target adapters for DAP, and the black wires are the trigger lines to be connected to some port pins here on the board. To show you how it works, I have a demo based on 2 applications, a master application running on core A, controller A, and a slave application running on controller B, and both controllers are communicating using HSSL. And there is a signal which is received by core A, which makes sure that controller B is still alive. And in the first example, I show you how we can debug, or we cannot debug this application if we not do or if we not synchronize both controllers for debugging. So I load the workspace for this non-synchronized mode. So in this case, we load the application for both cores, and we see we have 6 cores here visible. 3 cores belongs to controller 0, and 3 cores belongs to controller 1. On the right side, we have code of controller 1, and here code of controller 0. If we start the application, we have to make sure that we start at first controller 1 and then controller 0. And before we do that, I'd like to show you the run control setting, which is quite important to understand this application. We have here 2 run control groups. Each core has its own each controller has its own run control group, and so we do only synchronize the core itself, but not the controllers together. So we have here controller 0 and here the run controller of controller 1. And that's the reason for that we have to start controller 1 at first and then start controller 0 at first to make the application running as it's expected. And if we now set a breakpoint, for example, here I have prepared one in controller 0, in controller 1, then we see, okay, we stop here in controller 1, but not in controller 0. And that's the problem. If we stop here as well in controller 0, at this time, we are in a function or in a piece of code where we are now in a while loop that is indicating that we had a communication error between the two controllers, and we cannot recover from here anymore. And this is not that what we want for debugging. So if we stop here in this case in controller 1, then we crash the application on controller 0. That is not what we want. Okay, so a breakpoint in one MCU does not stop the other MCU, and the MCU A is running into a timeout. So that's why we need some kind of synchronized debugging, so that our both MCUs are synchronized. And this I'd like to show in the second example and the last example for today. And now we see it looks like quite the same, but the Multicore 1 control has only one group, and in this group, all the 6 cores of the controller 1 and controller 0 are coupled together and is prepared for synchronized run control. And if I now start the application and enable the breakpoint here at the same position, then instantly we get halted also in core 0. And from here, we can do some single steps. You see also on the right side, the controller 1 is doing also single steps. And sometime, okay, here is the timeout, which is decremented. And if we set a breakpoint here and go to the breakpoint, then, okay, here we receive the trigger at this line, and we can do stepping from this position and also disabling the breakpoints. Okay, and then we are in a safe state. So if we would look at the board, there are 2 LEDs now blinking, which are indicating that everything is fine. Okay, so that means if we hit a breakpoint now in one MCU, the other MCU is triggered as well and stopped as well. So we prevent any timeouts in this case. And that's the reason why we need some kind of synchronization for multi-controller debugging. Okay, then let's sum up today's webinar. I have shown you how to set up a debug session from scratch, which is very easy to have a workspace or to get a working workspace for the first steps with UDE. Then I have shown you the basics of multi-core debugging, including how the user interface looks like, how to synchronize breaking, stepping, and rerun the course, and what are the idea behind multi-core breakpoints. And then in the second part, I demonstrated the multi-controller debugging that we have, including the hardware setup, what is needed for multi-controller debugging, and what are the differences between non-synchronized and synchronized debugging. That's all for today. Thank you very much. If you have any question, then drop us an email or use the webinar panel. We will answer these questions offline, perhaps next week. And then in the series of the 5 webinars, the next webinar will take place on May 14th at 10 a.m. And it's about multi-core debugging for ARM Cortex-A and ARM Cortex-R SoCs. Thank you very much.